Okay, as usual, like I will start with a little bit clarification / correction. So last time, I guess I have hard time to spell out that word like moving average. So therefore I take up Wikipedia. So more precisely, so I see like there's lots of different kind of moving average. So I just want to kind of correct myself, make the name exact. So according to Wikipedia, it will be like exponential moving average or exponential weighted moving average. It is reasonable. So you have a form like part of this path. So basically, like exponential moving average, like of this y here in this case, for this s is the exponential moving average, and then you have a factor some portion from y, the current y, and some portion for the previous s. So if you elaborate that one, you will get basically this way. You just keep on substituting st equal to this guy many times. You expand like a long sequence, and then you also have an alpha at the beginning, but alpha is actually equal to 1 plus 1 minus alpha plus 1 minus alpha squared and so on, right? So therefore it's actually a weighted average that your weight is like exponentially decaying as you go to the past. So anyway, that's just a kind of clarification of what we have last time. So we talk about what, like at the end we talk about optimizers, and we talk about dropout and batch normalization and some data augmentation, and I guess what I'm going to continue to, honestly I'm quite excited for today's lecture because I spent like half of a day yesterday to prepare for that. Like I didn't expect that because I was thinking to use the old stuff, but then I look into that. I want to take a little bit details. So basically okay, maybe I just add a little bit like what we talked about last time. So all you remember, like we are all doing basically gradient descent, right? So just like you can think of it as like first order optimization, and all of them will involve like a learning weight. Basically, like you know the direction to go down, you need to decide like how far you want to go down for that one. So typically the learning weight can, you need to do a lot of massaging for this learning weight really. We'll talk a bit about that like after, I guess by the end of today's class. But just give a little bit ahead of time, like for example, you may have like step decay, like you may have learning weight that keep the same, and after a while you're just going down like by half, and you may have like exponential decay, and like you basically you can also have 1 over t that kind of decay and so on. So, and what I like to talk about today mainly is like about second order optimization. So as I mentioned, like for the optimizer we talk about, we basically just use the gradient, right? So now if we want to be faster, at least like in theory, like each step, if we want to go more accurate, if we can take advantage also the second order in multivariate case would be like the Hessian, right? Basically it's a second derivative of your objective function with respect to all the variables. So then given that, like let's say if you can make the Taylor series expansion, then you can immediately get the optimum problem, right? Because like the optimum problem will be just, okay, I want to take the minimum will be just taking the gradient, or like I should say like taking the gradient of this right hand side and set it to 0, right? So this is basically just a constant, right? Because okay, theta 0 is a constant, so it's a constant does not depend on theta. So this is I should say more precisely, it's a gradient with respect to theta. And for this guy, this is a linear with respect to theta, right? So if you take the gradient for that, you basically get back something like kind of gradient of j theta 0 of j at theta 0, And this guy, if you remember, like if we take gradient of that, we get like H plus H transpose times theta, times theta, right? And I also have a 1/2, but then of course like H and H transpose is the same thing. Sorry, I have a theta. Let's see, I'll make sure. Yeah, I think it's correct. So, but H. Sorry, I don't have theta here. Just H and H transpose, right? Let's see. No, that's a theta here. Sorry. So this is a theta star here, basically. And then like H and H is symmetric, so therefore H plus H transpose, okay, it's basically the same thing. So this guy cancels, it's just H here. So therefore we'll have the equation like that. We set this to 0. I mean, this plus this guy equal to that. So therefore you have, actually, that's a theta 0 missing. So therefore we have like, theta star minus theta 0 is equal to gradient minus H inverse gradient filter J theta 0, something like that. So therefore you move this to the other side, you get this. So but what you can see, like, okay, this what's so nice about this update actually? Do you see anything really nice about this update? Compared with like the first order optimization method that we discussed last time. Yes, we don't have a learning weight here, so it's pretty nice. Like we don't have this hyperparameter we need to design, so we just immediately kind of know, if assuming that this is a kind of this second order approximation, so it's like a ball, right? So we know right away where's the minimum there. It's basically, okay, we know the exact minimum there. Then at this point, at this function, at this point, you have another approximation for the hyperbola, or like, I mean, you think of like if one dimension will be hyperbola, yeah, and then you keep going down and so on and so forth. But the problem is like typically this step is killing you, because think of that, if you take the inverse of a matrix, the capacity will be in the order of n cubed, right? So if the matrix of size n, n by n cubed is, and think of what is the size of this H. The size of this H is essentially the dimension n here is the number of parameters, right? So a typical neural network will have, a deep network, you will see 1,000,000 parameters. So then it's like million to the cube. So this is like basically too much. So some method to try to kind of tackle this problem are so-called like Cauchy-Newton's methods. So in the sense that we are not computing this inverse Hessian like exactly, but instead we will try to approximate that like with some rank. Actually, that's a typo like in the CS231 and slides. It's actually a rank 2 update. So there's also rank 1 update algorithm. The rank 1 update algorithm is not BFGS. So and in that case, you will only need like n squared capacity. So we'll spend some time on this, because it's a wasted, but I spend like kind of like, I don't know how many hours, like 6-7 hours on this, so I'm kind of excited to talk about this actually. So one thing that I was surprised when I prepared for this one, I don't think I found lots of resources on this. So my rule of thumb of learning new stuff is always like hunt for videos first. I'm a lazy reader. I look for videos, then I look for PPT and potential online courses. Online courses, maybe I can find something. If you're looking for courses, we'll talk about this stuff. Most likely a appropriate course will be like numerical optimization. But I didn't have time to actually hunt down for courses yet. So I just go for videos and PPT and so on. But PPT, I cannot find very nice PPT, honestly. I find a couple of them. They talk about numerical optimization, but they only briefly mention BFGS. Even though actually BFGS is considered the state of the art for like second order optimization. And I need to really give credit to this video. This is by some Russian fellow. He gave a really amazing presentation on this topic. It's like only 30 minutes, but he didn't go into all the details, but he gave all the main steps there and kind of helped me understand this thing a whole lot. Because I first looked up also the Wikipedia, that page to me it's not very helpful at this moment. I mean, it basically just say, okay, if you want to compute, apply FPGS, you just go for this step and then this step and this step. It doesn't have a very good explanation or rationale for that. So again, okay, that's so much story about this, about I'm trying to learn this. And also I should mention about this lecture notes is by some fellow in UT Austin, and the notes is decent, yeah, but I still like the video more, and also like from these notes I found this book. Actually, this book is very nice, but unfortunately I don't know why the notation is pretty weird to me. Like it just have the approximation of Hessian as H as B, and then the inverse Hessian as H. So to me it's like pretty confusing. I don't know. So therefore I won't stick to the notation. Instead I will just say like the Hessian is H, then I will say the inverse Hessian is like B. And so the main idea is pretty simple. So you have a co-solution method. Basically what we are going to do is, okay, think of because we have the Hessian equation, right? So we have something like this one here. So let's say I have an inverse Hessian, and I know the gradient here, this gradient vector here. So then the direction I should go should be like, should be just equal to this multiplied by this, right? Because the direction is equal to theta star minus theta 0, right? So I will just call this the direction vector is dk here, and then the gradient is gk there. So at the point of interest. So then this dk here would be the current approximation of the inverse Hessian, and then like what we are going to do is keep updating this bk here, and then when we know the direction there, we will do a nice search. So we know where to go, then we will basically try to find the minimum somewhere there. So I won't talk about, there's some algorithm for that, but I won't talk about like live search today. So I focus on how to find basically the B inverse and B and H here, and then afterward then we can just have the new location, right? We have the new theta there, then we compute the gradient there, and then we update the gradient. So then we also update the new Hessian. So it will according to the how far we go, and also like the difference of gradient. So the gradients from the previous step, the difference of gradient from the previous step, and the difference from the previous location. So just this high level, like any questions here? Yes. Say it again.
In the
yes.
second step, the alpha is still like the numeric.
Okay. This one won't be like hyperparameter anymore. Like it was just pointing. Okay, this direction. Unfortunately, I didn't dig into that algorithm. Maybe next time, if I'm interested or like have time, maybe dig into another. So there's an algorithm like just okay. If I know it's this direction, I can just. Of course, if you do it dumb, maybe you can. I think like one way is like you just search far and then like you iteratively go back, something like that. But I think that's smarter algorithm for that. In the textbook actually, yeah. But I didn't look into that yet. So but if you're interested or like you guys are interested, this can be a project also. Yeah. Actually, I think this is the fun part of my job. Like as academia. It's like sometimes you just find something and you're kind of studying, and then like it's kind of interesting, and then you never know that, and then like you have a motivation to try to learn that, and then just explain that in class immediately, and that's I guess it's like kind of like a little bit privileged, like you have a long time learning experience that you can keep learning new things. So any other questions? So if not, then I'll just describe how to update the hashing. To begin with, like we will not go directly to the BFGS algorithm, but we'll look at like, okay, we just try to use a rank 1 update. So that's what the Stanford course mentioned. Like they say rank 1 update, but actually that one is not BFGS. So because like hashing, you think of that as just derivative of the gradient, right? So therefore, like my essentially, I will have a kind of like a approximation like this way, because if you look at that, this is basically I mean like the next gradient point. So I mean like if you move from you have the hashing is essentially is the derivative of gradient. Okay, I'm not sure, like it's apparent right here. This is that apparent to you guys, like this thing here? So this is just something like, okay, if you have f function f, you have the derivative there. So at x there, then I would say like fx plus x delta x is equal to fx plus f pi x times delta x, right? So because you have derivative is more or less like that, fx plus delta x minus fx over delta x, right? So if I just move the term, right? So this is totally just like one-to-one correspondent to this guy. So yes. So then like now the key idea is that I would just make it exact, and I make it exact like this is actually also known as the secant equation. So that means that like I would just have h multiplied by this guy is equal to, I have this now represent as pk, and then like is equal to like qk here is like gradient of theta k plus 1 minus theta gradient of theta k. So and with this secant equation, so now the update, what we are going to do is kind of magical. So think of what, okay, I just try to do any updates, but unlike I want to do a rank 1 update, then the rank 1 matrix will be represented by something like that, right? So any rank 1 matrix can be put as like just U times V transpose. Right? So then with that form, I just want to make sure that like this will satisfy this secant equation here. So therefore, this guy multiplied by pk is equal to qk, and then I can just rearrange the term or have u something like that. Qk is this put in the other side. Then I have u is equal to this here. So u is given at least, but then v can be anything here. But note that like we have another requirement, right? Basically, your hashing has to be symmetric and also has to be positive, semi-positive definite, or like positive definite. I guess it's more stronger condition. So actually it's okay to be semi-positive definite, I think. So then like one simple choice we can pick is like, let's say pick like v just as equal to this part here. Then you have like uv transpose apparently will be symmetric, right? So it's just like some constant multiplied by this vector v times v transpose, right? Apparently this guy is symmetric. Then so therefore we will have an update something like that. So is that clear for now? Any questions? So this is not BFGS yet, but this is like a way to go to BFGS, I would say. Just so if not, let me move on. So remember that, okay, in the equation there, we actually need to use the B or the H inverse to get updated, right? Because like we actually should have the direction there. We want to know the direction there, and if we actually we have the gradient there. And of course, as I mentioned, original motivation is that we don't want to find the inverse Hessian, right? So therefore, we actually want to find the H inverse. Here, I will use the notation B for H inverse. Actually, it's the same notation as the videos in the Russian by the Russian fellow. And then like so note that like if we think of if we define B as like inverse H there, then we will actually have a approximate direction. Okay, and then like when if we have that, basically if we want to approximate the direction, it's simply this one, right? Actually given earlier, it's given earlier, just this one here. So it's a little bit maybe here, and actually we don't need to invert this matrix directly, and even more, we can write down the equation immediately, because note that like what we are doing in the previous slide is basically saying that like if we have a constraint of this guy here, we can create a reasonable update for HK simply as this, right? And with like V equal to this guy here. And now like the only difference is that instead of I have like HP is equal to Q, I have like BQ is equal to P, right? So I can write it down immediately. I don't even need to rederive anything. So the update rules will be simply like BK plus 1 equal to this guy, right? So I have some new dummy variable here. So let's say instead of V, I put W here, and P here we should be Q instead, right? And also like W now should be like Q minus BQ, BQ, right? P minus BQ. Yes. So clear? So again, this is still not BFGS yet, but it's coming. So as I mentioned earlier, like BFGS is actually a rank 2 approximation. So what we earlier is like rank 1, so it's like we have like the current H is updated by like the previous H plus a rank 1 matrix, right? So if we want to generate a rank 2 matrix, then what we can do is something like this, right? So we have like U, W, 2 variables. Each of these will be like rank 1 matrices. And so now we need to decide like what we should put in there. So here I need to be hand waving there. But I will give another technical explanation why we will come up with this, but I won't derive for that part. So this one here, so we need to think of like, okay, what is the U and what is the W, right? So what would be a good choice for that? If you look at this guy for rank 1 update, we have these vectors. This rank 1 matrix is what's the word for that? It's created by like some of these vectors we here, right? So if I want to generate 2 rank 1 matrices reasonably, so one reasonable choice will be like pick U as Q and W as this part, right? Because if you think of that, you generate this rank 1 matrix here, you are kind of linking this two originally like what I'm thinking, like if you start with like rank 2 here, you can imagine like this rank 1 matrix is more or less like taking these 2 vectors, link them together and consider them like at the same time. So if I generate like a rank 2 matrix, then a reasonable choice would be I will break down this V into like 2 different components, right? So let's say if I just do that, then I will have update something like that, right? I have HK plus 1 plus 1 over alpha, and U, let's say it's like QK times QK transpose. Yes, QK times QK transpose, and 1 over beta times like HPK times PK transpose, HK transpose. Now again, I need to satisfy the secant equation earlier. So therefore, I multiply the whole things by PK here, and I want this equal to QK. And so by inspection, so one easy choice for alpha and beta will be, okay, if you look at that here, I will have this guy is equal to QK, right? So if I have this one, get this one got cancelled, then I'm good. So therefore, like if I pick a choice, I want beta, and note that this is actually a scalar, right? So I have I'll call a row vector multiplies by matrix and multiplied by column vector. So if these two are the same, then, or like this guy over beta equal to -1, then I will have this one got cancelled, right? So therefore I pick beta as this one. And similarly, this guy, I can pick alpha is equal to this guy here, then this will be exactly equal to QK. So therefore we will have an update rule like this. And so here, like I have now a update rule for H. So what I want to do is I want to find the inverse for that for HK plus 1 given as a inverse of HK. So here I will use the Sherman-Morrison formula. Basically it's like this one. I think you may have seen that before. Something like if you have a matrix plus a rank matrix that is composed of like U times V transpose, and if take the inverse is equal to this guy here. So it's quite easy to prove. Like let's say you assume this is the inverse, so therefore if multiplied by this guy here, so if you just expand that, like actually this multiplied by that have this guy here, and this multiplied by that have this one, and then like A transpose get removed, and then so for this part here, this guy can pull out 1 plus V transpose A inverse U, and this got cancelled, so therefore like eventually equal to identity. So okay, so if I try to use the formula there, recall that I have this Morrison formula here, and I have this update for BFGS, and I will call this class as D, and then let's try to do that. And I have basically like, okay, just try this inverse first, like D inverse will be equal to that, and I can write it as here, and then this guy will be equal to D minus this guy inverse. I can use this formula again, and then like, okay, it doesn't look too well, and then this part have here some common term, this guy here, the D inverse HP here also have D inverse HP, so therefore I try to compute D inverse HP here. So it turns out equal to this guy here. If you substitute this back to here, it cancels one term here. So anyway, what I want to say, that's where I gave up. And I try to look for in the book and other places, they will just say, okay, if you use the Morrison formula, you should eventually derive this and have this nice form like this. So actually, I'm giving out a bounty here. Anyone who complete this algebra will give 3% of the. So I cannot find anywhere that actually. But yeah, I'm too old to do this kind of algebra, so I really cannot. Like I gave up somewhere here. But I'll trust the book and the notes by the other guy. So therefore, like, you will have a B inverse update, B update, or the Hessian inverse update as this guy here. And remember the trick we did last time, I mean in the previous one, when we do the rank 1 update, we just, actually, let me continue, like, give a summary for BFGS first. So this is a summary of the whole algorithm. Therefore, basically, we'll kind of initialize the Hessian approximation. So if you know the inverse Hessian, then of course you will just initialize the approximation that you have. Otherwise, you can just use the identity, and then, like, you start with k equal to 0, and then randomly start with some starting point there, and then you compute the search direction, right? You use the approximate, get the search direction, use line search, and then afterward compute the pk and qk. That's basically difference of the location and difference of gradient, and then use the BFGS update rule for the inverse Hessian. So then you just repeat the loop until you are satisfied. Basically, if the gradient of the current point is, like, small enough, then sorry, I think this would be less than. So if, like, it's small enough, then you will just stop. So, but as I mentioned, like, in rank 1 update, if you look at the equation, I also can use the same trick. You remember I used the rank 1 update, right? So if I think of, like, I have an update rule for h using deriving from an equation, like the second equation, like hp is equal to q, I reverse the equation. Like, if I consider the inverse Hessian, I have, like, bq equal to p, right? So therefore, like, actually I can also have an update rule like this, right? It's a totally reasonable update rule. And it turns out, like, this update rule is an update rule for a different algorithm called DFP. It's an older algorithm that's considered to be worse, like, compared to BFGS. And now it's, like, a little bit some theoretical load. I would say, like, some PTA, but more technical explanation of BFGS and DFP. When we do the rank 2 update, like, compared with rank 1 update, we have more degree of freedom, right? So actually we can impose more requirement. So besides, we need to make sure it's symmetric and positive definite, and also, like, need to satisfy the second equation. We can also, like, enforce each update to change, like, the difference to be not so big. So more precisely, we can enforce, like, the BK plus 1, the next approximation, next Hessian, inverse Hessian approximation, compared with the current Hessian approximation, the weighted forbiddance norm to be as small as possible. Take the minimum. So the weighted forbiddance norm is basically like this. So it's, like, weighted by a matrix like that, and, like, take the forbiddance norm is basically take the square of each of the elements. So it's just some square, basically, of independent element. So when you if you expand this, it's basically just you have the W essentially weighted each of the element. You have W multiplied by each of the square of the element, and you sum over that. It turns out that I'm not going through this, but the difference of BFGS and DFP is just that you're using, like, different W here. So for DFGS, it's using, like, W is equal to H, and for DFP, you're assuming, like, W equal to H inverse. So how am I doing with time here? So one thing, like, if you look at this here, if you look at the BFGS algorithm here, that still, like, have some I shouldn't say problem, but some difficulty when applying to, like, large neural network. basically like each time you need to store this Hessian approximation, right? And still, like if you have a million parameters, this will be like a million by million matrix. So typically, nowadays I don't think you can store it in any machine. So so one way, or like one I'm not sure saying improvement or approximation is so-called LBFGS. It's like a limited space, like BFGS. So it doesn't store the complete estimate of the Hessian, or inverse Hessian more precisely. Instead, like, okay, if you think of the equation there, so when you do this update equation, you are just using the curve like, okay, if you think of like, B, okay, think of PQ and B. PQ, the size are much smaller than B, right? Because like, for P and Q is just a vector, right? So if you have a million parameter, the size of P and Q is just a million. But this one is a million square. So therefore, instead of storing B, you can simply store in PQ, right? But of course, if you just use P for estimate, it won't be good, right? But you can iterate several times, right? I mean, like, you can store like the last, maybe like several like P and Q. And then you start with like the very last and iterate this step. And of course, like in that case, you don't have a B, you can start with an I, right? You just assume the first one is I. Then you just use this iterative equation, let's say R times. So then, like, of course, there's a trade-off here. So compared with the previous algorithm we just described, you need so much more time, computational, time to compute the update here, the BK here. And also, apparently, it will not be as accurate because, you don't have the, you didn't use, essentially, the previous one, you use all the possible P and Q. Here, you just use the previous R of them. But, of course, the storage requirement will decrease, like, drastically. And, so, that's more or less what I want to talk about, like BFGS and LBFGS. Actually, I don't spend as much time as I'm kind of, okay with time. And, LBFGS, like, there's some issues still, like, kind of like pretty active research area. It's like, if you're using full batch, you're kind of doing okay, but if you use mini batch, or like you only use part of the data to compute each of the update, LBFGS like still does not work very nicely at this moment. So this itself is still an active research, but like if you have like smaller problem, does not have as many data points, let's say, then actually it's good to use like it could be better to use like LBFGS comparing with like first order optimizers. And for example, like there's some new style that I'll show you later on. Is basically you do some art, like have some image and kind of do some cheeking, like make it some very funny images. You will see like next time, basically, or maybe I don't know whether we'll do it today. So for that one, you don't have much training data there, and then you can use like LBFGS. And of course, like this is like kind of like active research area. So I really want to say, like, if you guys are interested in this kind of area, like this is actually very cool areas, because like this can give you lots of impact. I just checked like Adam like yesterday or something like that. It's like paper 2015, right? The citation is 6,000. It's crazy. 6,000 is the order, like number of citation is more than all faculty members in this department, basically. Last time I checked, your advisor actually have the highest like citation number. I guess it's about 6,000, but their one paper is 6,000. So it's I mean, like, if you really come up with, like, this kind of, like, good optimization algorithm, or maybe, like, some improvement of LBFGS, like, the impact is amazing. Yeah. So, that's almost it. That's just repeating what I just said. Like, if you're just, using this as packages, like, just for some particular application, like, you can always just start with Atom, and then, like, if you can manage, maybe you don't have too many training data, you can use the full batch, then you can also try BFGS. And okay, last thing that I probably will talk about today is like how to babysit your learning process. This is also like more or less extracted from CS231N. I think like the previous offering, like, it's even explained better, like when Andre Kampafi was there, like, he didn't die. I mean, like, he just, okay. I'm not sure you guys are aware of that. Like, it's amazing, like, all this, of course, like, officially this course, like, CS231N is taught by, like, Feifei Li, but in practice, actually, all the courses are, except the first lectures, are taught by his students, like PhD students. And, Andre, like, used to be, like, in Stanford, but he graduated recently. I think he's in OpenAI. Is that the name of that company? I guess, like, oh, shit. I forgot, like, who's the boss of Tesla? I suddenly forgot his name. Yes, yeah. I think Elon Musk is investing in that company. I don't know whether the company is owned by Elon Musk or, like, it seems to be, but anyway. So okay, okay. Let me get back to here. So in practice, so you have a problem there. You could be spending lots of time trying to train a good neural network. Maybe you already have the network in mind, but still, like, you may need to check lots of stuff. So, of course, like, first thing first, I remember that, like we mentioned, we need to pre-process the data. Typically, we just need to make it zero mean, and we may not even need to normalize that. You may try to normalize that too, but it probably doesn't help too much. Then afterwards, you need to design your architecture, right? So let's say in this example, what he did is, like, he just picked a two-layer neural networks. So it's just doing a CIFAR 10, like, you know, it's like just digital recognition data set. And so therefore, the outputs have, like, 10 different digits, like 10 different outputs there. So, okay, then to start with, like, a good thing to check is, like, you probably want to even before starting to train your network, you may want to just, like, check whether your loss function makes sense. So, you can, assuming that you do the weight randomly, right? So then, like, your model should be pretty diffuse. Then, you can compute let's say the loss there. And for many cases, you will know that what's the loss there, right? So, I keep forgetting, like, how to say things. What's the loss function we used earlier beside margin loss? You guys can help me? No, that's the log P minus log P. What's the name for that? KL divergence. Yes, but what? There's a formal name for that. Okay, cross entropy. I need to see a doctor. I know. So anyway, for example, you know, like, you have 10 classes, right? So if your model is kind of random, So expect like the output of all your classes is basically like same probability, right, more or less. So therefore, in this case, no matter what you put in, the probability should be 1/10, right? And you know the cross entropy loss there is like basically log p, right, minus log p, right? So therefore, you can compute that minus log p is like log 10. It should be approximately 2.3. So okay, you can at least, okay, it's 2.3, good, right? At least this is the first thing you want to check, right? Whether okay the loss function it makes sense. Then the second thing you can do is that you can crank up the regularization if you have some regularization. So remember the regularization will just add some terms to your objective function, right? So if you're cranking it up, apparently your loss functions will go up, right? So you may also check that, okay, it went up, it's good, right? So next thing, now we can start training this. And I think they give a very good recommendation. I find that it's very useful. I think we mentioned this also. It's like, you probably want to try to overtrain your model, overfit your model. Don't get too confident. So you think, okay, I'm invincible and write this code. This shouldn't have any, bugs here and there or something like that. So you always want to just give a very tiny data set and make sure you can overfit your model. So in the sense that like you should get like perfect accuracy. So for a very tiny model, you should just like curve fitting, right? You give a reasonably complex model, like a high complexity curve, like, right? And then like you only have few data points, you can fit the curve like completely, right? So then, okay, let's try that also and make a small model there, like just take like 20 examples for training. And then, okay, accuracy can go all the way to 1. So that's good also. That's a good sign. And that's probably that all of you should try, should do before you even try to test your model with like train your model with really big data. Always try to overfit your model first. Then, so then we can try to train now. So, we can try with a small regularization and try to learn. Learning weight is something really important. So, and we want to make sure the loss actually go down. So then, like, for example, in this case, it put some learning weight like 10 to minus 6 here. So it kind of barely going down. So if it seems that like, okay, it's not changing, then probably the learning weight is a little bit too small. So now, actually, one thing maybe like to point out here. Do you see why I'm not sure you can see it clearly. The cost is not going down. The cost is still like 2.3 something, almost the same thing here. But the accuracy is actually going up from 0.08 like to about 0.2, 0.19. Can you think of a reason for that? So actually what's probably happening here is like, remember the cost, like how it's computed. The cost is defined as like minus log p or something like that, right? So you may have like 10 classes, the probability doesn't change, but you have like one of the true class that have the probability go up a little bit, just a tiny little bit. So therefore the cost function doesn't change much, right? But then like when you compute the accuracy, you only count the one that actually is the maximum, right? So then it could be like the class that is actually correct have tiny little bit higher probability than the rest. So therefore, like when you count that, just count the accuracy, that one you will count as correct, right? Even though the cost barely changes, but that one will from like basically incorrect to correct. So you see what I mean here? So therefore, like the accuracy does improve, even though like your cost function actually doesn't change and doesn't change much here. But anyway, this is a good sign here. The whole thing here, it looks quite normal. Just like maybe learning weight is probably still too small. Then, okay, this one is just go crazy. Let's say he just try to shoot up the learning weight to like 10 to 6, and apparently it won't work. And then like, okay, it just get a bunch of NaN there, and this typically is a sign of like the learning weight is too high. So and then like things just get exploding, and so now then what typically wants to do is like, okay, we should just set a range. Now just keep trying. So we need to find a good learning weight. So and that will be like involve some kind of like cost validation there. So for example, like I can try a range from like maybe 10 to minus 3 to 10 to minus 5, and okay, so this will be the cost validation there. And okay, one thing like you probably want to do is like you can start with say something fit cost search. So maybe I start with like 10 to minus 3 to 10 to minus 5. Then I get to somewhere that, okay, it looks like 10 to minus, like 2 times 10 to minus 4 is pretty accurate. Then I'll just in that region and continue to do a final search there. And so in practice, you always want to use a log scale for your parameters. So you want to a uniform scale won't be too good. So like here, you use a log scale here. So and it try different hyperparameter here. So have different combination of learning weight, and also I think so we have some regularization here. Regularization parameter here, so and the corresponding like validation accuracy. So okay, this several are pretty good, like pretty high here. And if you look at that, the okay, let's see, this look like here, and then maybe like what's the range here? So we have like 1 to 10 to minus 4, minus 4, minus 4. Then it looks like the learning weight probably in the region somewhere like 10 to minus 4 to like maybe like 4, 5, 10 to 5 times like 10 to minus 4, something like that. And and then like maybe we can just in this final range and then keep searching. Now then we do a fine search here. So the learning weight, what he said is like 2, like okay, instead of like originally like it's going going from 10 to minus 3 to 10 to minus 6, it's changing time to like 10 to minus 3 to 10 to minus 4. And then I keep searching again. So here, so this one is pretty good. So, but for him, he say that like, he think that this may be a little bit worrying to him. So, you guys have any suggestion why? Honestly, I don't think it's easy to spot this one. So, his argument is basically, okay, because the range is like 10 to minus 4 to 10 to minus 3, right? So this is pretty close to the upper bound there. So maybe like there's something like even better, like beyond the upper bound. So we need to be careful. If the peak is like near the boundary, then we probably need to refine our range, right? So this is like just common sense, basically. So one thing like really should point out is many people, like, if they actually, even I had the mistake, like when I was like many years ago, like when I did a master, I remember like I need to tune parameters also. I did I did mistake like that. Like when I have like multiple parameters, it's tempting to use like grid search, right? So you have like several parameters, then like maybe you just make a grid there, like for maybe have parameter x and parameter y. I have for x is like from this to that, and then for y from this to that, and just loop over everything. It turns out it's pretty bad idea. It's like really not a good idea. The reason is that like if you have many parameters, typically there will be like some parameters are not very kind of like important, and some parameter is like much more important. For example, here, like let's say I only have 2 sets of parameters here. So this is like not that important, and this is like the important one. So if I do a grid search like that, I do basically 9 different settings here, search through, then you can see that like I actually only, in terms of this important parameter, I essentially only try 3 different values here, right? But if I do a completely random search, I will go for much more different combinations along these important parameters. Like I try much more combination for these important parameters. So therefore, just remember this, like when you do parameter search, always make it randomly, like just what we did here. So just like do a search, like just randomly pulling things out, and then like for each of the parameters. So any questions here? So if actually there's some more slides from him, is I guess I'll just show it that basically I didn't do this. Like like it seems to me like it's pretty cool. If you guys eventually work a lot on deep learning and neural network, I guess you probably need to be like this also. Like you need to manage how your training process, because you cannot just like dump it and let it run. If you do some real research, because like it probably will take forever if you just wait. You need what he does is actually he just write a command center himself, and then like he kind of like distribute like all this combination of parameter settings like to different nodes, and then like he has like crazy number of nodes, and then like he'll check each of these, and then like okay, this one is running pretty good, I need to refine this one, and this one is not doing good, I should kill this, and then something like that. And okay, I guess this is maybe this one. What do you think about this one? This like it trained for some time, and then suddenly it start to actually this basically lateral design. Okay, I'm ready to get trained. So what do you think this might be? What might be happening? So this probably like a probably like bad initialization is a prime subset for this one. So actually Andre also like create a Tumblr for this. Like he put lots of these like loss functions online, and like basically like I guess this is more like art than science. Like if you really need to work on this for your PhD, you hopefully you go a sense of that, like how you should tune these parameters. Honestly, I don't have enough experience to guide you for this guy here, but yeah, I'm interested to discuss though, like if you encounter any problem. So so okay, this one is just like overfitting and stuff like that. Oh, okay, this last line I think I like to emphasize. This is a good one. So basically, another thing you like to check also is you want to check like how much you are actually updating. Sometimes it's hard to interpret like the size of your learning weight, but it's easier to see like, okay, what fraction of your weight is actually changing, like what's the percentage of your weight is changing, right? That one actually gives you a pretty good guideline. For example, like you probably want to within a range, for example, each step is like changing about like 0.1% or like 0.001, something like that. So this one you can basically just vectorize your whole weight, right? The entire weight matrix, and then compute the norm, and then like compare with like the difference of your against vectorize your whole the delta weight, and then like compute the norm and then take the difference. And I guess that's about it. So just summarize like of what we talk about. Okay, for several lectures now. Then we talk about BP actually the whole many lectures ago, and then like we mentioned, okay, nowadays like you probably want to start with value for activation, and like for your sigmoid, like use 10H if you want to try something else, and then like you need to do pre-processing, but it's not very important. Do mean subtraction like always. Deep weight initialization is very important. Use batch normalization if you can. Use dropout. Use atom. And if you don't have many data, then you can consider to use LBFGS also. And you definitely need to babysit your learning process for real-world problem. And make sure you don't use squeeze search like to tune your hyperparameters. And I guess that's the last slide. And I guess I will just